let us start this lecture 26 with a thought process, manipulative materialism makes a man maniac. And we will usually now recall what we have done in the last 25 lectures. If you look at 5 or 3 to 4 lectures, I talked about various aspects of propulsive devices. Then we spent around maybe 22 lectures around that on fundamentals of the propulsion. That means, what are the tools are required to analyze a propulsive device, right. What are those? One is compressible flow, then we talked about thermodynamics, right. Then we talked about chemical kinetics, and then you talked about combustion, right. Now, we have almost completed, of course, I can't say we have completed, but we looked at it, so that it will be helpful for analyzing the propulsive devices, as the course is tailored to look at fundamentals of propulsion. Therefore, I have given emphasis for the fundamental. Now, we will see how we can use those fundamentals principle for analyzing a propulsive device, both air breathing engine and non-air breathing engine. Non-air breathing means rocket kind of engines, right. So, what we will do? We will now look at how to analyze a propulsive device, particularly the thrust and the other performance parameters. So, let us derive an expression for air thrust pertaining to air breathing engines, and here I have considered a pod mounted engine. I mean, we are not worried about what it contains, what are the components. We know that air breathing engine will be various components like air intake, compressor, combustion chamber, turbine and nozzle. We are not worried about. We are saying that it is basically propulsive device or a engine or a propulsive duct, and which is mounted in a pod. That means, there are various ways the engine can be mounted to an aircraft, right. You might have seen engines are hanging from the wing, and it is mounted nearby the fuselage, right. And in fighter aircraft, it will be engine where it will be located, where close to fuselage, but on the front side, right. So, the air intake will go. So, there are various ways of mounting the engines, but here we are looking at general, what we look at basically pod mounted engines, right, and it is hanging right from the wing. And keep in mind that the fuel flow rate will be entering through that engines, I have shown here, and through this is the inlet, right. This is the inlet of this thing, inlet, and this is your exit of the engine. That means, some air will be entering in and it is going out, and of course, you will have to add some fuel, combustion will be taking place, and then you will add basically energy, you will be giving energy, so that you can get the thrust. Now, when air is entering, and what is happening here? It is going at a very high velocity. Suppose it is entering with a v, and then it is leaving with a velocity of v, which is higher. Why it is so? Because you have added energy into it, and you are trying to accelerate the exit velocity. And keep in mind that we have done some approximation here. Is it that it will be coming through that way, that whatever vectors I have shown? Of course, it will be true, right, provided I assume that is one dimensional flow, right. In real situation, there will be boundary layer, there will be some swirling, because from turbine it is coming. So, there all those things we are not considering. Please keep this in mind. And now, if I want to find out this thrust equation, I need to invoke the mass conservation equation, momentum conservation equation. For that, I need to place the control volume. Where to control volume, where to place this control volume is important. Of course, here it is very, I have shown here, right. but why I will put like this. For example, why my control volume will be just exactly at the exit of the engine, why not it is far away, why my this control surface bottom and the top control surface is away from the engine, why not nearby or just here itself. And similarly, why my this left hand control surface, why it is in this place far away from the inlet, what is the reason? I can place control volume anywhere, right, is not it? Can I not put it here somewhere, or can I not take this as a control volume and then do that? I can do, yes or no, but if you do that, maybe analysis will be quite complex, right. To have a simplified, we have done that, and keeping in the one dimensional flow in mind, because if I use two dimensional, it will be little complex to do that, right. That is the only thing. And keep in mind that we are not considering the unsteadiness, that means it is not like taking a somersault by an what you call fighter aircraft, which is be unsteady, right. It is a label flight what we are considering to deriving this thrust, right. Okay. Therefore, we are considering the aircraft is moving steadily, right. And some other assumption we will be doing, but as you go along you can note down the assumptions, but I will not be stating as I had done earlier, like steady flow process, irreversible, right, there is no frictional effect, right, or Eulerian flow, all those things I am not stating in a very systematic way, but as I go along I will tell it, and some of the things I will not be stating very explicitly, right. So, why I am placing this control surface here, because as I told you here I can assume the flow to be one dimensional, but if I place somewhere here in this zone, then can I do that? If I do that, then the flow will be two dimensional nature, because it is a jet flow, entrainment will be there, and the flow, it is a wake region, right. So, therefore, it will be difficult to talk about. So, therefore, I will put it here where I can assume the flow to be uniform at the exit, and also the other portion from here to there it will be uniform, and we are assuming that it is this flow is coming with the same velocity with which it is entering the control volume at the inlet. That is the station 1, and at the exit I am saying station 2, and keep in mind that this surface is far away, because the effect of, because if I take a streamline over here, what will happen? It will be taking the shape of the things, and then I am having two dimensional flow. If I take this resolve it, one in x direction, other is in the y direction, right. So, therefore, it will be two dimensional. If I over here I will be not considering, I will just say that this y dimension some flow will be coming out, because there is obstruction, but that will be negligible, we will see that, and it is placed here so that the flow can be taken uniform, and I am not worried about how much it is, because if you know that actual flow will be little diverging in this zone in the inlet, because the envisaged flow will be there, and it will be diverging toward that. So, let us now look at considering steady flow process. The continuity equation becomes what you call rho v dot n dA, right. And if I take for this control volume, first we will take the mass flow rate through the engine. If you look at what is the mass flow rate, it is entering, if A I is my this area, right, then I can write down that how much mass is going out from the engine, that is rho e V e, and this is my area what you call A e, right, I have shown here A e. So, rho e V e A e minus rho v, because it is entering with the rho and velocity v with this, and rho v A I is the capture area what I call, and minus m dot f, because some of the fuel is entering, right, because whatever the fuel is entering, whatever the mass is entering, you will be going out of this, right. Mass is conserved, that is the exit mass flow. So, if I want to write down in a mass form, I can say mass flow rate of exit, this is basically if you look at m dot E and this is your m dot I and this is m dot A, that means m dot E is equal to m dot I plus m dot A. You can say this is basically mass flow rate of air plus mass m f, I can say that, right. That means, how much mass flow rate of air is entering into the engine. So, now we will be invoking the continuity equation for the entire control volume. What we have done till now, we are considering the mass conservation for the engine, that means, how much mass is entering, how much mass is going out, and that is the mass leaving the engine is equal to mass of the air entering into the engine plus mass of the fuel. It is a very simple one. Now, what I will do, like we will be considering in this domain, that is and how much is going out here and how much going at the exit. So, if you look at how much is going at the exit, that is rho E in this from the engine, rho E V E A E, right, and in this region what you are doing, like that is coming with the same velocity. This is again an assumption, because nearby it will not be, right, because of streamline it will be having different values, but however we are assuming that V. So, that is rho V into area. What is that area? Total area from here to here of the control volume, right, cross sectional area is A and the exit area A E. So, therefore, this portion, if you look at this portion is nothing but A minus A E, right. So, are you people are getting or not? For example, I can say that like this is my A, right, this is the A E and this is what you call, this is basically A. So, what this area is nothing but A minus A E, right, that is the through which this is coming. So, rho V V A minus A E plus m dot S, and m dot A is will be coming like like this in the y direction, sorry x direction, like this is the x direction. We are assuming that y direction will be very very low as you go away, that kind of thing, whatever the, but that is not true, it is an assumption, some component will be there. Then clubbing this what you call, clubbing this equation 1 and equation 3 we can get, because we are interested to find out what is m dot. So, I can write down m dot S is equal to rho E V E A E plus rho V A minus A E, right, minus, right, plus rho V A plus m dot F, right, because I am taking this left hand side, then I am getting that. And what I will be doing, in place of this m f, I will be writing rho E V E A E, that means in place of this, or in place of, I will be writing basically. Now, what we will do, we will just put this in place of m dot F, we will use this equation 1, that is nothing but rho E V E A E minus rho V A I, and the same thing as rho E V E plus rho V A minus A E. Keep in mind that I have left one term here. So, I will add it rho V A. If you cancel it out, this term will go away, and similarly this term will go away with this term, right. So, what I will get, I will, if I simplify, I will get m dot S is equal to rho V A E minus A I, and if you look at, I will get m dot S is basically I can get rho V A E minus A I. This will be rho into what you call A E minus A I. That means, this is the amount of mass flux which will be going through this control surface, right, and the down of course up, like it will be going out because there is a body, and we will be using this and find out an expression for a thrust. So, that if you look at the thrust wise, keep in mind that this thrust is actually acting over in this direction, but when we take this from the cut from the what you call pod, then the reaction to thrust will be in this direction, right. So, now what we will do, we will be using this momentum equation and we are neglecting the body force, right, which is will be very small to be neglected, and we are considering momentum equation along the x direction only. So, we will when we will do that for a steady cases, we will say this total flux is equal to some momentum flux is equal to summation of the f x, the force along the x direction. So, what are the forces acting on the x direction? One is the thrust, right, which is along the x direction, and what are the other forces are acting? Drag we are not considering, right. Right, is a label, right, thrust is equal to the drag, right, am I right or wrong? So, what else other force will be acting on the control volume, because we are using a control volume, what are the other forces will be acting? The pressure force, right. So, what will be pressure force in the this surface? This will be what you call like P into A whole surface and same cross sectional area. Similarly, what will be pressure force which will be acting here in the exit? That will be P E and A E, and whatever this annulus area leaving this exit portion, if you take it as a circular, right. So, what will be there? That will be the pressure force which will be acting over in the opposite direction to that, right, which will be P A minus A E, right, which will be opposite to the x direction, right, in the this way. So, then we can write down that the thrust force or the summation of the force along the x is thrust plus P A minus P A minus E, right, and minus P E A E. So, if you simplify this, what will say, this will be cancelling it out, right, with this. So, you will get T plus A E P minus P E. Now, we will be evaluating this term like momentum flux term for this control volume. So, you will do that, then what I am getting? I am getting m dot E V E plus m dot S, right. This is the mass flow rate and which will moving with a velocity v, right, because it is far away. So, it will be moving this fluid along the x direction, right, that is an assumption, because we are assuming along the y direction that mass flux is negligibly small, right, plus rho v square A minus A E, that means this amount of which will be there, right, because we are considering in the exit, and what about this? This also rho v square A minus A E, this term, minus what is the inlet? Inlet will be m dot A v in this region, right, minus rho v square A minus A I, right, because if you look at this amount is entering into m dot A into v, but in this annulus region it will be rho v square A minus A I, because this is A I, right. Keep in mind that A I need not to be same as A E, okay, need not to be, it may be same, it may not be. So, if I now put this equation 4, right, into this place, right, and simplify, I will it will cancel it out, I will get m dot E V minus m dot A V, right. And when we substitute this expression over here, this is basically equation or equation 5 like this, I will get thrust is equal to m dot E V E minus m dot A V plus A E P E minus P A, right. So, if you look at this is the expression for the thrust, and what you could see there are this is basically momentum thrust, right, and what is this? This is your pressure thrust, right. And if you look at this is basically is the exit, this portion is your exit thrust, and this is what? This is inlet drag, right, that is inlet drag, because that is a acting, like whatever thrust being produced by the jet, right, is being swallowed by this inlet drag, and one has to reduce it as much as possible, right. Then what will gain? If my velocity, the flight velocity is 0, then what I will do? I will be only on the land, right, okay, but I may get a thrust. And keep in mind that this thrust can be maximum values, right, and this thrust can be maximum when it is fully expanded. That means, if the nozzle is fully expanded, that is P E is equal to P A, that is fully expanded nozzle, right, okay. Then you will get the maximum thrust, okay. Now, what we will do this, we will now substitute for m dot E, because we know what is m dot E? M dot E is equal to m dot A plus m dot F, right, that we have already derived. When you substitute these values, I will get thrust is basically m dot A plus 1 plus F V E minus V plus A E P E minus P A. How I am doing that? Because like F is basically m dot F by m dot, this is the fuel air ratio by mass, right. In place of m e I am putting, I am taking the m dot A out. So, I am getting that. Keep in mind, this is a very small number, generally it is a very less than 1 kind of thing. So, sometimes and rather majority places we will be neglecting it, right. When we are discussing now, I am like onwards, several places we will be neglecting. We will say that F is very less than 1, therefore, it will be equal to 1. What is the number F? Can anybody tell me what is expected? It will be around 25:1, it can be 30, it can be kind of things, right. That means, it will be 1 over 25, right, or 30. That means, air fuel ratio will be 30:1, like fuel air ratio will be 1 over that. It is a very small number. So, we can neglect that, and this expression, if I in the case of rocket engine, this will be V will be 0, right, and then I will get this 0, then I will get a thrust expression as m dot E V E plus A E P E minus P A, right. We will be discussing little bit more about when we will get into rocket engines, right. Maybe I will invoke this expression again and talk about some of the things. So, what is the difference between non air breathing and air breathing? Only that inlet drag will be there and the expression is similar, right. Now, we will be looking at engine performance parameters. What are those? There are several efficiency we will be defining. So, first we will discuss about propulsive efficiency, right. And what is that? That is basically ratio of thrust power to rate of production of kinetic energy of the exit jet, because you are basically, that is why you call it jet engine, or a jet propulsion. In some places people talk about it, we use, because the kinetic energy and then from that we will be getting the thrust power, right, is a ratio. So, mathematically if you want to look at, you can write down thrust power means thrust into velocity, that will give me thrust power. This is nothing but your thrust power, and the thrust power plus the amount of energy which is going out in the exit, right. And keep in mind that this is what, this portion is the kinetic energy which is being what you call being going out, a mass into this change in kinetic energy is going out, right. So, this if you look at, we are looking at with reference to what, with reference to the earth, right. If you look at this, if I look at a kind of a vehicle, like let us say this is a vehicle engine which is going, this V E and it is entering with V, right. So, there is a person over here, right, and with reference to that how much V is changing, this mass, that will be changing m dot V E minus V whole square, right, that is the mass which will be changing. So, by ignoring the pressure thrust, and keep in mind that what we will be doing till now, we are not considering whether the pressure thrust is ignored or not. Now, we will be ignoring, we will say that it is fully expanded nozzle, that means P E is equal to P A in the thrust expression, and fuel mass flow rate being small, that means the F is negligibly small. From that, then what we will do, the thrust expression became, because what we have looked at, that is m dot A 1 plus F V E minus V plus P E minus P A into A E, right. We are saying this is 0 and this is also 0 F. It is not true, but we are saying for the simplicity. Then I will get m dot A V E minus, this will be equal to m dot A V E minus V. Actually, this is approximately equal, right. And this is my thrust and V is the velocity, that is the power, and then m dot A, and I will be using the same thing V minus C, and this is the whole square, because I have taken in place of m dot E, I am using basically m dot A. So, I will take it out, and if I simplify this thing, if I take V E minus V out of this place, what I will get? I will take this V E minus V. So, this will cancel it out, and this become V E plus V E minus V, right, divided by 2, and if you just simplify that, you will get basically 2 plus V E divided by V. What is indicating? It is indicating that the propulsive efficiency will be dependent on the exit velocity and flight velocity ratio, right. And when it will be 100%, when V E is equal to V, right. That means exit velocity is equal to the flight velocity, N P will be 1, right. That means 100% propulsion, is quite a great, Is it possible we can get that? So, now for the rocket engine or the non air breathing engine, equation 11 we can have, right, we can get the similar way, that is m dot E V into V E, because in the rocket engine what we are saying? We are saying that m dot approximately equal to m dot V E, because it is a fully expanded nozzle, we are assuming P E is equal to P A and there is no V, right. Flight, if you look at, no air is entering into engine, am I right. So, my thrust expression will be m dot simply V E, right. So, I am putting it here, and if I simplify, I will get 2 V E divided by V divided by 1 plus B by V whole square. If you look at, it is similar, but not same, that is the difference, that is this is a square is coming in the 1 plus V E by V square, and here there is another term is coming on the numerator. So, that is the difference, right. And in this case if I want to find out when it will be the propulsive efficiency will be maximum, that will be again V e is equal to V, right, am I right, because if I say this is 1 and this is 1, 2 by 2 it become 1 means 100%, more than that you cannot, because how much energy you are giving, you are all getting back in the or converting into thrust power. Is it really possible, right? That means whatever energy I am giving, I am just taking, I am just utilizing it to converting. If you can do that, that will be wonderful. I have already discussed that you will get maximum propulsive efficiency when V e is equal to V, right, exit velocity is equal to the flight velocity. Now, let us look at for a air breathing engine and little bit talk about the efficiency, what is happening, how it is changing with the velocity ratio, that is exit velocity and flight velocity ratio. Exit means exit from the engine, okay, and flight velocity of course in this case in the air breathing engine, the velocity with which the air is entering into the engine. So, if you look at, if I look at this propulsive efficiency with the V, you will find at when V e is equal to V 1, same you are getting 100%, after that it is decreasing. That means, when the exit velocity will be go on increasing for a particular flight velocity, right, what will happen, propulsive efficiency decreasing, right. That means, if I want to fly an air breathing engine, right, for a particular flight velocity, right, then if I go on increasing V, I am in trouble, because the propulsive efficiency is coming down. But if I want to, always we want to maximize the propulsive efficiency, am I right? But if I maximize, what happens? If V is equal to V, then what happens? Thrust will be 0. If I say this is 0, so or approximately 0 or in compared to, so I can say that thrust will be 0, m dot a V e minus V is equal to 0 for V e is equal to V, but propulsive efficiency will be 100% for this condition, right. That means, I am having trouble, right. If I go one extreme side, I am getting 100% efficiency, thrust is 0. If I go other way around, that is V e is far greater than the V, right, I may get higher thrust. If V e is greater than V, far better, like V can be negligibly small flight velocity, then I am getting the maximum thrust, right. But my propulsion, what I will do? It is like that what I started this talk, like if you are too materialistic or what I call stinkingly materialistic, then you will be in deep trouble, that what we are today. And if you say that I do not want materialistic, then you cannot survive. So, you will have to take a middle path, and based on these things there are several kinds of engine people have developed, right, jet engines. What are those? That is basically what are the jet engines, based on this concept. What are the engines you are aware? That is ramjet, turbojet, turbofan and turboprop. So, if you look at, I have shown you schematically, we will be again visiting, I am not really discussing about that, but what really is happening in the ramjet? Ramjet will be flying at a very what? High Mach number, and what happens to exit velocity? It is also equally high, right. That means, in this case what I will get? My propulsive efficiency will be very low, because if I want to fly at a high Mach number, then naturally I will have to give a higher thrust, otherwise I cannot, can I, for the same kind of drag, like I cannot. So, therefore, here propulsive efficiency is very low, and as you go on to turbojet, it is propulsive efficiency lower than the higher than the ramjet, but thrust will be lower than the ramjet, and turbofan thrust will be medium kind of thing, propulsive efficiency will be quite okay. And if you go to turboprop, propulsive efficiency the highest, but the thrust will be very low. So, you will be at a slow moving or something, we use a turboprop engine, right. So, we will be discussing about that, but let us look at now the rocket engines, right, how this propulsive efficiency varying with the VE by V. How will be it will be varying? Will it be varying the similar way that it goes on decreasing? Certainly no. If you look at this expression, you will find that propulsive efficiency is increasing from the 0, because I can have VE, right, or V may be very high as compared to VE, right. That means I am going towards 0, but in reality it is not possible, right. So, it will be of course from this expression is being plotted here. So, it will be goes on increasing till it reaches VE is equal to V, the velocity ratio becomes 1, and after that it decreases, right. Generally it is not possible to maintain this VE by V is equal to 1, right, because it will be all accelerating. So, therefore, people try to operate in this regime where propulsive efficiency will be very high. Instead of this region, people do not operate, although sometimes during the static, during the intake maybe sometimes, but that is a very small time. Now, we will be looking at thermal efficiency, because this is about propulsive efficiency, which will tell you how good your engine is providing the what we call thrust power. But now we need to look at, right, how good it is in converting the fuel or the chemical energy into the kinetic energy, because here what we are using, change in kinetic energy we are using to get the thrust power, right. So, that means this is, we can say that the thermal efficiency is the ratio of the kinetic energy into the amount of energy or the fuel being burned, and that means total chemical energy, right. If I just simplify this and then if I expand this one, you will get that is equal to m dot A VE minus V2 whole square. This is nothing but your kinetic energy, change in kinetic energy, divided by m dot F delta SC, right. So, keep in mind that here what are the assumption we are doing, because I am not using same as equal, because the same assumption we are doing, the nozzle is fully expanded, that means there is no pressure thrust from the pressure difference change, and also the m dot F is very much less than the m dot A, or F is less than 1, very less, right. So, that assumption we have made. But however, for the turbo shaft engine, we can't really talk about that kind of things, because the flight velocity will not be there. So, what we will be looking at, we will be looking at the, instead of change in kinetic energy, we will be looking at the shaft power, because in the turbo shaft engine we use the shaft power, right. So, therefore, I can use P, that this is basically shaft power, and m dot F delta SC, m dot F is the fuel consumption rate into SC is the heat of combustion, right. And keep in mind that we are assuming the combustion efficiency is 1, which we are not considering, okay, in this case, but in real situation it will not be. So, now overall efficiency will be what? Overall efficiency will be basically the propulsive efficiency and the thermal efficiency. In other words, it will be the thrust power, ratio of the thrust power and the amount of energy being consumed or being used for that. That is the thrust power m dot F delta SC, and you will find that you can derive this, which is very obvious, that propulsive efficiency into thermal efficiency. Now, question arises how it will be varying this overall efficiency with respect to, let us say, velocity or velocity ratio, right. So, what we will do, we will again assume the same assumption that F is very small, or the fuel mass flow rate being small. So, equation 14 becomes like this, what I am doing, m dot A VE minus V, I am using the thrust, and I will find out VE minus V into V F delta SC, right. And if you look at for a particular fuel air ratio or a particular kind of fuel, right, you will find that it is dependent on the V e and V, right, that is exit velocity and flight velocity. And what we will do, we want to find out what is the overall efficiency of a propulsive device or the engine, right, that is more important than that of propulsive only, propulsive efficiency, thermal efficiency. So, for that what we will do, we will differentiate this equation with respect to V, the flight velocity, and we will find that is equal to 0. If you do this algebra, you will get when the flight velocity is half of the exit velocity, you will get a overall high maximum overall efficiency, right, which is generally the case being used particularly for your Boeing kind of series. And we will see also why this long range commercial or the rather passenger aircrafts is being operated at Mach number of what? What is the Mach number it is being operated? 0.85 kind of things or 0.8 kind of things. Why it is so? This is one of the reason, but another reason I can talk about it. I think I will stop over here and then we will discuss this thing in the next lecture, and some of the more like performance parameter like static thrust and other things, right, and range, all those things we will be discussing. Okay.